Let's start with the part 2, that is interpolation and interpolating algorithms. Another method for generating arc is by using approximation or by using interpolation. Instead of using ready-made algorithm, we are approximating the curve by small straight lines. Approximation is nothing but interpolation. For this, we have to use Lagrange interpolation technique. The aim of Lagrange interpolation is to generate a smooth curve which passes through an ordered set of points. Generally, this set of points are called the control points. In this technique, the curve is approximated by a number of small straight line segments. It is possible to draw an approximation to a curve if an array of sample points are known. Then it can be guessed what the curves should look like between the sample points. The common theme is to use these control points to generate parametric equations. The aim of Lagrange interpolation is to generate a smooth curve which pass through the set of order points. We can draw an approximation to a curve if we have an array of sample points. We know that curve is a set of points or pixels. The sample points are nothing but some points on the estimated path of the curve. From this few sample points, we can guess the shape of the curve. If the sample points are closer to each other, we can easily guess a correct curve. Our guess may not be exactly right, but it can be acceptable one. Suppose we want to draw a curve of shape which is shown in this figure, and we are having a set of sample points as shown here. From the known sample points, we can draw a curve which can pass through the nearby sample points. Now we will try to fit the known curve in these sample points. We can fill the gaps between the sample points. For this, we have to find the coordinates between two sample points on the curve. And then we have to connect these points by using small line segments. The process can be followed. First step, fill in the portions of the unknown curve with pieces of known curve which pass through the nearby sample points. Since the known and unknown curves share these sample points in a local region, it is assumed that in this region the two curves look pretty much alike. Second step, fit a portion of the unknown curve with a curve that is known, which is shown in this figure. Third step, now fill in a gap between the sample points by finding the coordinates of point along the known approximation curves. That is, calculating more points from known curves. Fourth step, connect these points with line segments. Actually, draw straight line segments connecting these points. But how we are going to find the points which are lying on the path of the curve? Generally, to draw a line or circle, we need equation of line or circle With the help of that equation, we can find whether the specified point is lying on the boundary of that line or circle. After placing a point in the equation of line or circle, if that equation becomes true, then it means the specified point lies on that line or circle. For line, we are having equation y is equal to mx plus b. Similarly, for circle, we can use equation r square is equal to x square plus y square. Similarly, if we want to draw any curve, we must know the equation of that curve so that we can place a point in that equation, and if the equation becomes true, it means the specified point is lying on the curve. But here we do not know the equation of the curve. There are many forms of the function which we can make use by adjusting parameters to find the points between the sample points. Normally, functions are expressed in the form of y is equal to f of x. That is, y is a function of x. But to generate a curve by approximate method, we are using parametric form. So x is equal to fx of a, y is equal to fy of a, z is equal to fz of a. Here we are using parametric form because it considers all three directions equally and it allows multiple values so that curve can cross itself. Suppose we want a curve that passes through n sample points. Let's say x1, y1, z1, x2, y2, z2, xn, yn, zn, and so on. As we are using parametric form, the equation of the curve should be x is equal to fx of a. It means we have to construct some function for this curve. As this curve is passing from sample points, the function must be then summed and the n terms, that is one term for each sample point. Here, for each function fx of a, fy of a, and fz of a, we are using one common function bi of a. This function b of a is called as our blending function. To implement the curve drawing program, the same blending function values are needed for each section of the curve that is drawn. If each section is approximated by 3 straight line segments, then each section will require the blending function values for u at 0, 1 by 3, 2 by 3, and 1 as shown in figure. Here u is our a function which we have used for fx of a. To achieve a perfect curve, it must pass through all the sample points. It means each sample point tries to pull the curve in its direction. The first algorithm, set smooth, allows the user to specify how many straight line segments should be used to complete a section of the curve. The second algorithm, make curve, multiplies the sample points and blending function which generates points on the approximation curve. These points are then connected by line segments after a section of the curve has been drawn. The sample points are shifted so that the blending functions can be applied to the next section, which is accomplished by third algorithm, which is in next section. Given 4 control points, let's say P0, P1, P2, P3, space ranging from 0 to 1, and in between 0 to 1 we have to find the u function evenly. P0 is equal to P0 for the first point. P1 as given u P of 1 by 3, that is P of u, that is P of 1 by 3. Second point P2 is equal to P of 2 by 3. Third point P3, that is equal to P1. Putting this in interpolation equation, P of u is equal to C0 plus C1 of u plus C2 u square plus C3 u3. Apply the interpolating conditions at u is equal to 0, 1 by 3, 2 by 3 and 1. We get P0 by putting P of 0 as C0, P1 as P of 1 by 3 and C0 plus 1 by 3 C1 plus 1 by 3 square C2 plus 1 by 3 cube C3. P2 is equal to P of 2 by 3, that can be given as above equation P of u, that is C0 plus 2 by 3 C1 plus 2 by 3 square C2 plus 2 by 3 cube C3. P3 is equal to P of 1 is equal to C0 plus C1 plus C2 plus C3. So by these equations, we can calculate the rest of the points which are lying on the curve. This is an example of interpolating algorithm by using technique interpolation. Interpolating polygon. The blending function can be used to round the sides of a polygon. It is easier to deal with a polygon since no special initial or final section occurs. We just step around the polygon, smooth out each side by replacing it with several small line segments. We start with a polygon that has only few sides and end up with a polygon which has many more sides and appears smoother as shown in this figure. We can also interpolate polygons by using our blending functions. The sides of any polygon can also be rounded rather than the polygons are easy to handle. We just step around the polygon, smoothing out each side by replacing it with several small line segments. We start out with a polygon that has only a few sides and end up with a polygon which has many more sides and appears smooth. Next section we will see B-splines and corners. B-splines or corners. First, B-splines. Question can be asked, explain B-spline curves. Give at least two properties of it. Spline curves. We have already seen interpolation technique to generate a smooth curve. It must pass through all sample points. It means the sum of blending functions must be 1 for every sample point for integer values of a. We may get blending function as 1, but for fractional values of a, we may not be able to pass the curve through the sample points. The B-spline blending functions were designed to eliminate sharp corners in the curve. In this method, the sum of blending function is not 1 at every value of u. The blending functions were designed to sum at 1 for integer values of u and not a fractional value. Each section of the curve is connected to the next section at a sample point. It is not necessary that the slope of two sections match at this point. Thus, we do not get a completely smooth curve if there are corners at the sample points. To get the smooth control over the curves must be pulled onto the neighborhood of sample point, rather than force it to go through the point. Then the result will be a curve which follow the general contours indicated by the sample points, but may not actually pass through the points. A set of blending function which follows the above approach and always sum to 1 are referred as B-splines. The following is an example of 5-segment B-spline curve. The points which indicate the ends of individual curve segments and thus the joint points are known as knots. Each curve segment is determined by 4 control points as follows. From P1 to P4, we are having one control point, C1. From P2 to P5, we are having another control point, that is C2. From P3 to P6, we are having another control point, that is C3. From P4 to P7, we are having another control point, that is C4. From P5 to P8, we are having another control point, that is C5. In next section, we will see the remaining part. We will stop here. Thank you.